So let's see. The first problem set is due on Wednesday. We will have our problem sessions on Tuesdays at 2 o'clock in room 190. Okay? Now we can try to power comment for those who are at external locations. Anyway, but that's the deal. And we'll try to work out another office hour for those who can't make it to this time. All right. So has anybody tried or failed or succeeded to download notes and/or stream video from the website at this stage? And no problems? Are there? Good. The videos work?
Videos are
Cool. Excellent. Okay, good. So, let's get started. So last time we were talking about the so-called Stark effect. The Stark effect is the shift and perturbation of the energy levels in the presence of an electric field, of an externally applied electric field. And for the moment, we're talking about the so-called DC Stark effect, meaning static electric field. At some point, we'll talk about the AC Stark effect when you have an oscillating electric field. Okay. So the generic problem is a kind of perturbation theory type problem where we have our unperturbed Hamiltonian and some interaction or perturbation Hamiltonian. In this case, we're talking about the perturbation to the energy levels to hydrogen or hydrogenic atoms, but the Stark shift, of course, we talked about the Stark shift of quantum well states in a heterostructure semiconductor. It's the same basic physics. So we have our zeroth order Hamiltonian, we have our perturbation, which is the interaction of the electric dipole moment associated with the atom and the interaction of that dipole with the applied electric field. And so the dipole moment is an operator, which taking the nucleus, in this case the proton, at the origin, so R is the relative coordinate of the electron relative to the proton at the origin, the electric dipole moment operator is just the charge of the electron times the position of the electron, okay? And for concreteness, let's just take the electric field to be in the z direction. So this is our perturbation Hamiltonian or interaction Hamiltonian. And so as we discussed last time, we under the assumption that the electric field is sufficiently weak, which means something small compared to 10 to the 8, 10 to the 9 volts per centimeter, which is most electric fields you would apply at a static field, then this is a perturbation, and we can do perturbation theory. And so to lowest order, the shift is just given by the expectation value of the interaction Hamiltonian, and that's 0. And that's 0 because the mean dipole moment of the atom in one of the eigenstates is 0. It's 0 for the ground state, and it would be true for any of the eigenstates specified by n, l, and m. And as we discussed last time, that is a reflection of the fact that the eigenstates of the Hamiltonian are eigenstates of parity. And since the position operator, or the dipole operator, which is just proportional to it, is odd function, then it only has matrix elements between states of opposite parity. Okay? So there is no first order shift in the ground state of hydrogen. So we went to second order, and second order perturbation theory, the shift depends on the off-diagonal matrix elements relative to the energy difference of those states. And so we plugged all that in. First, the other thing we noted last time, and we'll re-emphasize this over time, is that this dipole operator, or its proportionality, only has off-diagonal matrix elements, or matrix elements of any kind, between states for which L differs by 1. Okay, so L has to be odd because of parity, delta L, but it has to be 1 because this is a vector. Okay, so that's a reflection of vector operators. We'll talk about that, the Wigner-Eckhart theorem, etc. Something which I hope you have seen in 522, but if you haven't, we'll talk about it. Moreover, the only non-zero matrix element is the one with between the ground state, which has m equals 0, and the excited state, which has m equals 0, because we've chosen to look at the dipole along the z direction. And that's a reflection of the axial symmetry. Okay? If we had taken the electric field along x or y, we would have had, and we will show, off-diagonal matrix elements only for m being plus or minus 1. Okay, so that has to do with the so-called selection rules that we'll review later in the semester. So we did that, and it turns out that in this case the sum can be done, and we arrived at this expression for the shift in the ground state of hydrogen. Shifts down by an amount that depends on the square of the electric field, and thus this shift is often known as the quadratic Stark effect, because the shift is quadratic in the electric field. And that's because we went to second order perturbation theory. Okay? We had to. And as I discussed, one of the things, of course, we always know, the first thing we should do to see if our solution makes sense is, are the units right? So that's a question of developing some notion of intuition about the units of electrodynamics, which no one has any intuition anymore about. But we should develop some intuition about that. So electric field squared is an energy density. And this is an energy. Energy density means energy per unit volume. So we got volume times E squared is energy, so that's good. So we did the right thing. All right, so now what I want to do at this stage is to think about, we did some math. Let's think about our physical intuition about this problem. What is this shift representing? How do we understand this physically? So let's think about classically. What do we expect? Meaning the following. I can think about a classical description of something like an atom, right? Where I think about my electron as a charge density, probability cloud is a charge density, and I have my protons. So I have something which, loosely I might say is, I have the electron cloud, which is spherically distributed around the nucleus, right? So this, of course, has no mean dipole moment because the electron cloud is distributed equal probability all directions from the center. And then, let's try to make this a sphere. And then we apply an electric field in the z direction. So what does this do to the atom? Well, it's going to polarize this atom. So in this case, before the mean, the average dipole moment averaged over the charge distribution, or the dipole moment of, it's really not the average in some sense, it is the dipole moment of this charge distribution classically is 0. But when I put on the electric field, what's going to happen? Well, I'm going to shift the negative charge relative to the positive charge. So to the degree to which it just shifts but doesn't distort the shape, which is kind of the first order thing that would happen. The electron cloud would move up, would move down because the force is opposite to the direction of the field because the down electron is negatively charged. Because we had, it's Ben Franklin's fault. I always blame him every time. Why he made the electron negative is enough to give us all heartburn for decades and centuries to come. If only the electron were positive. But c'est la vie. We're stuck with it. So the electron moves down. And this is, a problem that's a kind of classic E&M problem, which is what's the electric field inside of a sphere, right? That's uniformly spread with charge. And you could calculate what this is, it's in Purcell's book on freshman electrodynamics. It's a great problem, everyone should do it. Anyway, the point here is that what happens, of course, is that I have an induced dipole moment, which is in the direction of the electric field. And so now we can ask how big is this induced dipole moment? Well, I can think this picture again, there is a force on the electron here that's going to be proportional to its displacement from the origin. So a picture of this is to think about a charge on a spring. And this is the classic Purcell problem of, how big is the restoring force and all of that when I have a spherically symmetric charge distribution. I won't go through that, but you could do it. The point is, this is a charge on a spring. So I can think about this as, here's the electron, it's on a spring. I apply an electric field, and that effect of that electric field is to displace the electron and compress the spring a little bit. So there is a induced equilibrium position of the electron due to the balancing between the restoring force of the spring and the applied force of the electric field. So what we have to do is just equate the equilibrium position. This is Hooke's law, has to equal the Coulomb force. Okay? The magnitude of this, right? So the magnitude of my position here is E over m squared times the electric field, which says that the induced dipole moment is equal to E squared in the direction of the electric field, because the dipole moment measured, because this is a negative charge, the dipole moment is up, so it's in the same direction as the field. Okay? So, what we see is that the induced dipole moment is proportional to the applied field, and that proportionality constant is what's called the polarizability. Okay, how polarizable is this bound set of charges? And that polarizability depends on, well, the binding is kind of varied in terms of what the natural frequency is of the oscillation, and alpha is here. So now the question is, how much potential energy is stored in this system when I have applied this electric field to this bound set of charges? Well, the potential energy is a combination of the potential energy stored in the compressing of the spring together with the potential energy associated with the new charge distribution, right? When you have charges in fields, there's potential energy associated with that charge. So my potential energy here is 1/2 m omega squared times the position, which is the equilibrium position. And then the potential energy associated with the dipole, which is in the presence of the field, well, I now have minus d dot E. Okay, so that's the total energy. So this is equal to 1/2 m omega squared E over m omega squared minus d, which is alpha, which is E squared over m E squared. E squared, I guess I forgot my E for it. Okay? So this is the potential energy in the spring, and this is d dot E. So what I see here, this is minus 1/2 E squared over m omega squared E squared, which is minus 1/2 d induced dot E, which is minus 1/2 alpha E squared. Now this is an often forgotten fact. If you have a polarizable particle which does not have a permanent dipole moment, the energy is not minus d dot E, it's minus 1/2 d dot E if you have an induced dipole moment, because half of that energy went into the spring. And it has to be that way because what's physical, energy is in some sense a construct. What's physical is dynamics, and the dynamics is the force. So this is just a basic review of electrostatics. Force on a dipole in a field. The force is d dot grad E. It's something you get out of basic electrodynamics. Okay? Now if E is proportional, if D is proportional to E, because it's an induced dipole, then this is alpha which is equal to minus grad of minus 1/2 alpha. Let me call this for dE just to be consistent. See this half? Now, if this were a permanent dipole moment, well, then I wouldn't have that half there. Okay. All right, so what was the point of all this? So classically, we can understand the energy associated with the redistribution of charge in the presence of electric field as I get an induced dipole moment, and then that induced dipole moment interact with the field, and the energy is equal to minus a half the induced dipole moment times E, or minus a half alpha E squared. Is that the same? I mean, the only issue is is this the same physics that's going on quantum mechanically as classically? And the answer is yes. The effect of the electric field is to redistribute probability amplitude, and therefore charge distribution inside the atom, to induce a dipole moment. To zeroth order, there was no dipole moment. And then that induced dipole moment interacts with the field and shifts the energy. So let's calculate, see what is the induced dipole moment quantum mechanically. So, quantum mechanically, what we want to know is, what is the induced dipole moment? And that's, in other words, what is the expectation value of the dipole moment operator in the presence of this field? We said it was 0 because of parity considerations in the absence of the field. Now in the presence of the field, what is the induced dipole moment? Well, to do this, we need to find out what is the new wave function, or the new state of the system in the presence of the field. So this is equal to the expectation value of the dipole operator in the perturbed ground state, which I'll call psi twiddle. So what is the perturbed ground state? Remember, the ground state is change in the presence of the field, and perturbation theory tells us how to calculate what that new ground state is. So we go and we dig in the depths of our memory or our textbook, and we remember that if I want to calculate what the induced, or the new state of the system is, it's the state to zeroth order. This is unnormalized. Plus the sum over all the excited states in other words, recall that the effect of the perturbation is to admix, as we say, which is really add superpose, not statistical mixture, but we always call it an admixture because that's the way they called it back in the 20s or 30s or 40s. A little bit of the other state into the initial state. Okay? So in this case, from the selection rules, as we discussed just before, the same thing as before, this is equal to the charge times E, and there's only the P states that are so for consistency, let me call this psi and phi. So the effect of the perturbation to lowest order is to mix in a little bit of P character of the excited states into the ground S state, and thereby create a non-symmetric charge distribution, which ultimately induces the dipole moment. Okay? So let me call these coefficients, I'll just put all of this stuff together, Cn prime. Okay? So now we can calculate what the induced dipole moment here is. This is going to be equal to the sum this way. And then I have to normalize it, right, because this was unnormalized. And this is going to be something like 1 plus order Cn squared stuff. All right. Now, keeping to lowest order in this perturbation, which in this case, in the numerator, remember the only off-diagonal matrix elements are the ones between S and P. The P states have no diagonal matrix elements. The S states have no diagonal matrix elements. It's only the off-diagonal matrix elements between S and P that are non-zero. So that's stuff that's first order in C. So I can drop this lowest order in the perturbation. And rewrite my equation here, where C sub n prime is equal to E dot okay, so that was my little admixture there. So when I plug that in, what do I get? What I get is the following. This is equal to 2, where my electric field in the z direction, I have one matrix element from C sub n prime and one matrix element over here, right? When I plug in for C sub n prime. Let me see if I got my signs right. I think I did not. Yeah, it should be a minus sign because there is this minus sign over here. Okay? So, in fact, there's no e squared, it's one factor of e. Just this one factor of e. Excuse me. And so what we see here is that this is equal to alpha e, as expected. So the mean, the induced dipole moment in the z direction is proportional to the electric field in that direction. And this is the polarizability of hydrogen in the ground state. So this is the polarizability. Generally, as we have classically, the polarizability is a tensor. But here, we have a spherically symmetric wave function. So there's no tensor. You push on it in any direction. You know, which direction is z? I have no idea. It's spherically symmetric. So it's just a scalar in this case. And with this, we can then see, in fact, that from this, what we see is that the shift of the energy is equal to -1/2 alpha E squared. That's exactly this expression. This is exactly the expression we had doing first order perturbation theory. I'm sorry, second order perturbation theory. So the physics is exactly the same. We have a polarizable particle, we put an electric field, it induces a dipole, and that induced dipole moment is proportional to E, and then that induced dipole interacts with the field, giving us that expression for the field. And that's the quadratic Stark field. So one of the lessons here is one shouldn't forget about physics. It's not just about here's a Hilbert space, here's a POVM, here's an information complete. No, there's electric fields and there's charges and things. We should think about the physics of the system and to check that what we get gives us some deeper intuition about what's going on. Alrighty. So, let's see. So now what we want to do is think about second order let's think about the Stark shift on excited states. So let's think about the n equals 2 energy level of hydrogen. Now, at the level of description that we have right now, the n equals 2 energy is multiply degenerate, right? The degeneracy under this level of description is n squared. So there are 4 sublevels associated with that energy, right? What are they? Well, we have for n equals 2, we can have L equals 0 or 1. That is to say, we can have an S state or a P state. And for the P state, we could have M sub L equals -1, 0, or +1. In this case, we can only have M sub L equals 0. So these are the 4 sublevels, all associated with principal quantum number 2 in hydrogen. So, you will recall that when you have degeneracy, you have to be much more careful about doing perturbation theory, because obviously such an expression will diverge because the energy denominators will be zero if you sum over degenerate states. So, what we remember from perturbation theory is that when I have a degenerate subspace, then, in some sense, all orders of perturbation matter within that subspace. Which means that when we have our Hamiltonian expressed in terms of a zeroth order piece and an interaction piece, what we should do is diagonalize in the subspace. Now, one should note, of course, this distinction between degenerate and non-degenerate perturbation theory isn't a digital distinction. Suppose the difference in the energy levels was 10 to the minus 100. Well, for all intents and purposes, well, what does that mean? Well, you have to talk about in sense of units. The question really is, how big is the energy scale associated with my interaction Hamiltonian compared to the energy scale associated with H0? So, in this, when we come back over here, when we looked at non-degenerate perturbation theory, we saw that we start getting admixtures of other states with probability amplitudes that depend on the off-diagonal matrix elements of the perturbation relative to the energy difference between the zeroth order Hamiltonian. So if, just to emphasize some points here, if I have some energy spectrum which has some energy levels of some kind with some differences in the energy spacing. If this distance is, say, or any of these, the distance between the levels is huge compared to the energy scale associated with the perturbation, well then I can do perturbation on each level individually. But suppose it were the case, well let me put this guy way down here, that I had an energy scale that kind of is on the order of this splitting, but tiny compared to this splitting. Well then I would diagonalize in this subspace and then do higher order perturbation theory with respect to the other levels. So degenerate perturbation theory should also be thought of as near degenerate perturbation theory. And what near degenerate means is that you have two energy levels that are very close compared to the scale of your perturbation. Okay? Yeah?
So when these two levels are close
Yeah.
together, it will be more convenient for me to use it? Because certainly this expression mathematically won't blow up if I use it.
No, but it won't converge. So the question is this a small parameter or a big parameter? So what I generally have here, well, let me write it over here. What I would generally have, what's important here is my CNs here depend on this ratio. This is the small parameter. In order for this interaction to be considered a perturbation, this ratio must be small. That is to say, the off-diagonal matrix element of my perturbation must be a small energy compared to the zeroth order energy splitting between the two levels. When they start to be on the same order, well, then it's not a perturbation anymore. And then so these expansion coefficients, if you go back and think about where perturbation theory was right, it was a Taylor series expansion. You did some kind of convergent test. But when this starts to be of order 1, well then it's just not an accurate solution. You'll have a problem like that for homework to look at. Okay, so here we are. We have this degenerate subspace. And we have our perturbation. So again, our interaction Hamiltonian will take is minus d dot E, which I will take the electric field to be in the z direction, and this is then like this. So, according to perturbation theory, we need to diagonalize our Hamiltonian in this 4-dimensional subspace. Okay. The diagonal matrix elements are the ones we already know. In fact, they all have the same energy, the diagonal matrix elements, because it's a degenerate subspace. So, to diagonalize. H. So we have the 2s state, we have the 2p minus 1, we have the 2p 0, and the 2p plus 1. So we're using the shorthand here for NLM. Okay? So firstly, my diagonal matrix elements of the Hamiltonian. What can you tell me about this matrix element?
0.
It's 0, right? For the reasons we discussed before. these are eigenstates of parity. My interaction Hamiltonian is odd under parity, so these matrix elements, as before for the ground state, are 0. Okay, and of course these are all the same. It's minus 1/2 over n squared, or minus an 8 in atomic units. Okay? So now let's look at the off-diagonal matrix elements here. So we have well, first thing we know, of course, is that because these were the eigenstates of H0, there are no off-diagonal matrix elements of H0. There are only potential off-diagonal matrix elements of the interaction Hamiltonian, right? So this is going to be which in atomic units, this is the electric field in atomic units, and the length, the position operator in atomic units. Okay, so what can we say about these? Well, firstly, what we discussed before by parity, we cannot have a matrix element, an off-diagonal matrix element, or a diagonal matrix element for that matter, of the position operator between states of the same L. Right? So I can't have this matrix element is 0 for all states within this 3-dimensional subspace, right? So the only potential non-zero, this is 0, except for the state where one of them is a P state and the other is an S state. It's the only non-zero matrix element, or its complex conjugate. So, what can we say about this? Well, this is the same kind of matrix element we saw in the 1s state when we were looking at the ground state perturbation, right? We had first order perturbation varied, but then to second order we had off-diagonal matrix elements between the ground state S and excited state P. And there was only one non-zero M, which, I'm sorry, not non-zero M. There was only one choice of M for which this matrix element is non-zero. Let's review that quickly. We did that last time by thinking about expressing Z as a position, the position representation, and then rewriting the Z coordinate in spherical coordinates, and then re-expressing those spherical coordinates in terms of the spherical harmonics, and then thinking about the orthogonality between the different spherical harmonics. And from that, we saw that this was like a y1, 0. This was spherically symmetric, so the only case was the m equals 0. Let's think about this in maybe a slightly more general way. So let me do a little aside here. Consider a matrix element the z position between two states that have well-defined LSM. Okay? We know let me think about a rotation operator about the z-axis. So let me rotate about the z-axis by an amount phi. The rotation operator is generated by the z component of orbital angular momentum. The rotation operator acting on one of the eigenstates of angular momentum leaves it invariant. This is an eigenstate of LZ with eigenvalue m. So this is e to the minus m phi. Right? So let me look at this matrix element now and introduce into this the identity in the form of R dagger R. The rotation operator is a unitary operator, and R dagger R is the identity operator. So this is then equal to e to the I minus I phi m minus m prime L m. So this acting on this gives me that phase. This acting on this gives me the complex conjugate of that phase. And then I have left over R z R dagger L m. But the z coordinate is invariant under a rotation about the z-axis. That's why I chose to do this, because that is a reflection of this axial symmetry. So this must be equal to z. Thus, we see that since this must be true for an arbitrary phi, this matrix element is 0 unless m equals m prime, which is an example of a selection rule. The dipole matrix element for a dipole operator in the z direction only connects states with the same m value. Okay, we'll see this in great detail when we think about absorption and emission of electromagnetic fields and the way in which I can excite to different sublevels within an atom depending on the polarization state of the light. Okay? So, what does that tell us in this case? Well, this is a state with L equals 0, ML equals 0. That from what we've just learned over here, what is possible values of m prime for which this is non-zero? Zero, right? That's what you just said, ms equal m prime, right? So, the only non-zero term of all of the matrix elements, the only off-diagonal matrix elements are the ones that couple the 2s0 with the 2p with m equals 0. Okay? So this is 0 unless m prime equals 0. Okay. So from this we deduce the following. in the subspace of n equals 2, H has the following matrix representation. Now, when you write down a matrix, you have to think about the order of the basis elements. There are 4 basis elements: the 2s0, the 2p0, the 2p with m equals 1, and the 2p with m equals minus 1. Now, since the only states that have off-diagonal matrix elements are the ones with 2s0 and 2p0, it makes sense to order your matrix so that those 2 elements are next to one another. Because then you can see the form in a block diagonal way. So let's do that. I'll order this, put the 2s0 here, and then I'll put the 2p0 here, and then I'll put the 2p1 and the 2p minus 1. So, as a 4x4 matrix, what we see is that block and that block are 0, because there's no off-diagonal matrix elements between these guys and these guys. This guy is already a diagonal matrix element. It has and then I have this one 2x2 matrix up here. And that 2x2 matrix is, it has the same diagonal matrix elements. And then it has off-diagonal matrix elements, which I'll just for the moment call epsilon. Where epsilon is equal to it really should have an epsilon star here, but it turns out that this is a real number, so the off-diagonal matrix have to be conjugate to one another. Okay? So firstly, we need to calculate epsilon. How are we going to do that? Well, this is the case. You've got to resort to doing an integral. There's no other simple way, at least that I know of, with algebra, raising a lowering operator, or some other goodies that would allow us to calculate this matrix. We have to just resort to doing an integral. So, okay, and of course, we do these orbitals are expressed in spherical coordinates, typically. We could do it in parabolic coordinates, but we're not going to do that. And so this means we rewrite the z operator now is the z position, which is r cos theta, which is equal to root 4 pi over 3 r y1 0 of theta and phi. Okay? And so this then becomes equal to, when now expressed in terms of the reduced radial wave functions that absorbs the Jacobian 0 is y10 star, which is real, so it doesn't really matter. We have a y10 here, and then we have, oh, I forgot the r, that's important. We got, that's from here, y00 from the S state. And then we have this factor, 4 pi over 3. Okay? So, this is a constant. This is 1 over root 4 pi, so this whole thing is 1 over root 3. This integral is 1. Okay? Again, written in the wave mechanics way, the selection rule that we saw before in terms of the fact that we only had non-zero matrix elements if the two m's were the same, given the matrix element of z, is expressible in terms of this integral over 3 YLMs. So quite often you will see a selection rule described in terms of this integral over 3 YLMs. And this thing, well, you know, you just got to do it. There's no doing it, and that turns out to be equal to something. Is it 3 root? It's, yeah. This is equal to minus 3 root 3. Okay, so what do we got here? So this is epsilon. Epsilon is equal to this times the electric field in the atomic units. And E0 is equal to minus 8.
Do you have that 1 over root 3, or has that already been?
Oh, you're right. Thanks, Ben.
Sure.
Well, anyway, so. Great. Okay. So now we have our matrix. We need to diagonalize our matrix. Now here you're going to hear another diatribe from me. You just got to get a diatribe per lecture. Everybody should be able to diagonalize a 2 by 2 matrix in their head. Or at least should be able to do it without writing down, I do the determinant of lambda minus that, I take the polynomial, I take the roots, then no. You do not do that for a 2 by 2 matrix because you are physicists and you know everything about Pauli matrices. What are the eigenvalues of any Pauli matrix? They're plus or minus 1. So if I can re-express this in terms of a Pauli matrix, I can just look at it and I can tell you what the eigenvalues are. So let's do that. Here's our matrix. We only have to diagonalize this 2 by 2 matrix. Now, of course, we never have to, this is already, the first part is already diagonal, say identity, and it commutes with everything. So we just have to diagonalize the off-diagonal part, which is this. This is the identity. And what is this? This is sigma x. Remember your old friend sigma x? Here it is, sigma x. This has nothing to do with the spin of the electron. Nothing, not a darn thing. It's a 2 by 2 matrix, and every 2 by 2 matrix can be written as the Pauli matrices. So, what are the eigenvalues of this by 2 matrix. Anybody? What are the eigenvalues of sigma x?
Plus minus 1.
Plus or minus 1. So what are the eigenvalues of the whole thing, of this whole matrix thing? The eigenvalues are, the eigenvalues of this are plus minus 1. So the eigenvalues that's the eigenvalues of the eigenvalues. Almost all problems in perturbation theory are like this. Almost all problems of perturbation theory are the coupling of 2 nearby levels. And you can do it basically in your head. So these are eigenvalues. What are the eigenvectors? Well, they're the eigenvectors of sigma x, right? Because the eigenvalues of sigma x are also the eigenvectors of the identity operator. So, and the eigenvalues of sigma x are the symmetric and antisymmetric combinations of the diagonal. So the eigenvectors, I'll call 2 plus or minus, is equal to square root of 2 2s0 plus or minus 2p0. Those were the 2 states that were mixed by the perturbation. And what you see is they're completely mixed, right? You see, this comes back to your point about when we looked at the quadratic Stark effect, we had a tiny admixture of the p state with the s state, a tiny, absolutely tiny admixture that depended on the strength of the electric field compared to the electric field inside the atom. And that gave me the probability amplitude with which I mixed in a little. But when I have degenerate perturbation theory, I completely mixed the 2 states. And if I had near degenerate, they would be darn close to completely mixed, but it wouldn't be exactly 50-50 superposition.
Isn't that just, those are the eigenvectors of sigma x with it?
Yeah.
And then so you have some amount of the eigenvectors of the identity.
Which are the same, the eigenvector
Right.
of sigma x.
So
This
shouldn't-
diagonalizes, if I multiply h on this, I get E0 plus or minus epsilon 2 plus or minus. You only have to, you don't have to diagonalize the identity, you just diagonalize this part. The eigenvectors, this are the eigenvectors of the whole matrix. So if I have a general matrix, which is A times the identity, plus B vector dotted into the sigma vector, the eigenvalues of this are A plus or minus the magnitude of B. And the eigenvectors are spin up and spin down along the direction of B. In this case, it's like a fictitious B field in the x direction, and thus, so if you give me a 2 by 2 matrix, you can diagonalize it by writing it in this form, and then you just write down the eigenvectors and eigenvalues. All right, so where are we? Oh yes, we're talking about the solutions. So what we see here, though, is the following now. Putting back in what this is, this was minus an 8 minus plus 3e, right? Or with the units back in, this is minus an 8 e squared over 2a naught minus plus 3a0 e. So what we see here is that the energy shifts of the n equals 2 energy levels of hydrogen, the ones that shift to lowest order shift linearly. This is what's known as the linear Stark effect, as opposed to the quadratic Stark effect that we saw in the ground state. Why did we get a linear shift? So let's just sketch the energy levels of the system. So if this is the electric field magnitude, and this is the energy level, and this is the ground state, and this is the first excited state of hydrogen, what we see here is that, we saw this quadratic shift that we discussed at the beginning of lecture. But what about the excited state, the first excited state, n equals 2? Well, what we see firstly is that the lowest order, before we get to quadratic effects, the 2p plus or minus 1 and 2p minus 1 stay degenerate. And then we end up with a linear shift, a splitting of the energy levels that increases linearly or decreases linearly with the electric field straight, where these symmetric combination the symmetric combination goes down in energy, and the anti-symmetric combination goes up in energy. What's going on here? Well, this is an example of what, I'll give it a very heavy-handed name. This is what I might call spontaneous symmetry breaking. What do I mean by that? Well, what we mean by this is the following. The Hamiltonian commutes, or H0, commutes with parity. However, the states, which are the symmetric and anti-symmetric combinations of the S&P states, are eigenstates of H0, but not parity. So there are states, eigenstates of the Hamiltonian, which break the symmetry that the Hamiltonian respects. The Hamiltonian is parity invariant. Nonetheless, these states are eigenstates of H0, and that happened because they were degenerate. So I could, for all intents and purposes, without any perturbation, this is an equally good energy level. Now, such a state actually has a dipole moment. So even though the eigenstates S0 and 2p0 don't have dipole moments. The linear combination of them does have a dipole moment and is a perfectly good eigenstate of the Hamiltonian in the absence of an electric field. In the context of chemistry, this is sometimes what's called a hybrid orbital. So if I thought about this, I have the y00, which is the S state, and then I have the y10. The y00 is spherically symmetric. The y10 is antisymmetric. So if I put, now I'm going to write the sign of the wave function, not the sign of the charge, the sign of the wave function. This is everywhere positive, this is positive, and this is negative, right? Because it's parity negative, right? The YLMs have this kind of, if I have degeneracy, as in the n equals 2 state of hydrogen, then I can mix these two with plus or minus. So if I have a plus and I add them, then I end up with, I subtract a little here, I add a little here, I get an orbital that looks like this, where I've added these things together. Now this is not parity invariant, and therefore the charge density is located more up here than down here, and I have a mean dipole moment. So this is why we can have a linear Stark effect, even though the standard orbitals of the Hamiltonian have no dipole moment to 0th order. The hybrid orbitals, which break symmetry spontaneously, do have a dipole moment. So we have, in some sense, a permanent dipole moment associated with these hybrid orbitals. And that permanent dipole moment then interacts with the electric field to 1st order and gives me a linear shift. Now, to really determine whether one goes up or one goes down, one needs to also consider the sign of the radial wave function. This drove me nuts. On Friday, I was working, I was like, why, if I add these, now the electron goes up. So isn't the dipole moment like this? So shouldn't the symmetric combination have the positive energy? Why does the symmetric combination have lower energy? The symmetric combination is the one that the dipoles be aligned. So what the heck? I mean, it took me hours. I just couldn't figure it out. And then I said, oh, wait a minute. Of course, you have to talk about the radial wave function. And the radial wave function, that's just, you know, who the heck knows where those signs come from relative to what. But you have to multiply the amplitude of the radial wave function is negative for the 2s0. And so it flips it. You'll see it. I do a little Mathematica, just for my own sanity, and put it in the notes, which I'll post today. All right. So let's see. So that's where we are so far. Where we'll pick up next time is we'll now need to start including the important effects of spin in our description. And so we'll review some very fundamental aspects of angular momentum on the campus.